low pressure, molecules are far apart and the molecular forces have little to no effect for most of the time. As a result, this gas behaves almost like a perfect gas. At the moderate pressure, the attractive force dominates the repulsive force, causing the gas to be more compressible than the perfect gas. This is because these molecules are drawn together, reducing the volume more than expected under this ideal condition. And at the high pressure, in this region, repulsive force becomes dominant as molecules are forced very close to each other. Since repulsion presents the further compression, the gas becomes less compressible than the perfect gas. So this is how the real gases behaves under the pressure condition. So as the first step in understanding the pressure dependence of real gases, we introduce the compression factor, which is G. This quantifies the deviation from ideal gas behavior. So the compression factor is defined as the ratio of the measured molar volume of a gas to the molar volume of the perfect gas. Here, mathematically, the compression factor becomes a Vm divided Vm naught, where this Vm is the actual molar volume of the gas, but the Vm naught is the molar volume of a perfect gas. So using this definition, the perfect gas laws become Vm RTG. So as you know that the ideal perfect gas will say that Vm is nRT, and then if we divide it by this by n, this becomes the PVm now. Yeah, and we know that the compression factor is Vm naught, and then we just use this relationship to here. Finally, we can get the PVm equals is RT. So this is for your gas. This is for the perfect gas. And as you see that when the compression factor is 1, here, the gas behaves as a perfect gas because it follows the ideal gas law exactly. And let's see the plot of experimental value of compression factor for different gases. So if you see that at the very low pressure, this compression factor is close to 1, indicating that the gas behaves almost like a perfect gas since these intermolecular forces are negligible. But at high pressure, all gases exhibit the compression factor is greater than 1, meaning their molar volume is larger than that of the perfect gas because the repulsive force dominates this region, pushing molecules apart and making the gas less compressible. And at the intermediate pressure here, most of gases shows the compression factor below the 1, meaning their molar volume is smaller than that of the perfect gas because attractive force are stronger here, so pulling molecules close together and reducing the volume relative to the ideal gas. To describe real gases more accurately, we use the equation of state with the correction term, accounting for the molecular interaction. One of the most widely used model is the Fourier equation of state, which expands the relationship between pressure, volume, temperature into a power series. So this Fourier equation of state explains like two versions of variable, for example, pressure and then and the molar volume. And this equation, the first term of the Fourier equation is identical to the ideal gas law, where the compression factor G is 1. And let me talk about more about this equation. So in this equation, 1, B, C are the Fourier coefficients, which depends on the temperature actually. But in the case of third term, C is less important than B because it's quite smaller than this first and the second term. And if we wanna see more feature of this one, we will gonna use the derivative of G with respect to B, P pressure. So let's go back to the plot. So for example, here the slope of this plot is this derivative of compression factor with respect to the pressure. So if you see this slope, dg versus dp is 0 for the perfect gas. However, for real gases like hydrogen, the slope of this plot does not approach at 0 at even low pressure, since if you see this equation, it is not 0 for the real gases. So you can interpret this dgdp with this plot. But actually, I mentioned that this B and C or Fourier coefficients is dependent on temperature. So there is a condition where this B becomes 0. So there may be a specific temperature where the compression factor equals 1 with a 0 slot at the very low pressure or a high molar volume. So this temperature is known as a boil temperature here. So it's a little bit different the perfect gas, but you can see that the slope of this temperature becomes 0 when the pressure approaches is 0. So the meaning that this B is also 0 as well. And there is another temperature called the critical temperature. So at this critical point, as we calculate this plot, the isotherm merges to a single point without the phase separation. So this point is known as a critical point where the gas and liquid phase becomes indistinguishable. So here, this pressure is a critical pressure, and here it is the critical volume corresponding to this state. So above this temperature, like you can see the plot, the critical temperature here of this material is 31 degrees Celsius. So above this temperature, like in this region, they do not pass the liquid vapor coexisting phase. So the sample has only a single phase, which is called the supercritical fluid, that is not liquid phase but much denser than the typical gas phase. And below this temperature, like below this critical temperature, below 31 degrees Celsius, we already described the condensation of liquid, like liquid and the gas phases coexist in this plot, in this area. So I think you know PT diagram very well. So in here, this line represents the separating solid and liquid, and this line represents the liquid and vapor phase. So points on this line is a vapor-liquid equilibrium, and the critical point is the highest P and highest T. And this beyond the critical point, there is only one phase, neither liquid or vapor. So in PV diagram, is above the critical temperature, the phase is a supercritical fluid, and below the critical temperature, liquid and the vapor coexist here. So you can compare these two different diagrams. This is pictures. There are pictures near the critical temperature. As you can see at the below the critical point, you can see a clear liquid phase. And above the critical point, no liquid has been found. And when the sample is cooled below its critical temperature a little bit, you can see that the liquid phase reappears and see the unclear materials like here. So in previous slide, we have studied the gas behavior using the equation of state, but it is even more useful to have a broader perspective that applies to all gases. One such approach is the van der Waals equation, which accounts for the molecular volume and the intermolecular forces. So in 1973, the scientist van der Waals introduced the modification of the ideal gas to explain two key factors affecting real gases, such as the finite volume of the molecule, meaning that the molecule has a real volume. We actually assume the perfect gas as a point-like particle. It's a little bit different. And there is a attractive force between this molecule, like, because it has a mass, like here. So he considered these two factors and then make the van der Waals equation. Let's see this equation. So pressure in a gas, as you know, that depends on both the frequency of molecular collision with the wall or the force of each collision. So attractive forces between molecules reduce both the frequency and the strength of this collision, leading to the decrease in pressure. So the reduction in pressure is proportional to the square of the molar concentration and divided by V, and then finally expressed as A multiplied is mv square. So this means that the frequency of collision is proportional to this particle density, or strength of a collision, like pressure or force, is also proportional to this particle density. So the reduction which was affected by these attractive forces is proportional to this both term. And finally, there is a constant A, which means that the kind of a property that how the attractive force affects this reduction. And the second, as I mentioned, gas molecules have finite volume, meaning they occupy the space and cannot be compressed. So thus the V is replaced by the V minus mv. So mv is the total volume taken by the molecule themselves. With using these two real gas behavior, we can get the van der Waals equation here, right, like here. And as you can see, like A represents the strength of attractive interaction, and B here is represent the repulsive interaction when the molecular size is valid under the condition that molecules are close to each other. So if these attractive intermolecular forces are strong, meaning that A is large, the gas will exert less pressure than an ideal gas under the same condition, since attractive forces reduce the collisions. Conversely, if repulsive interactions are stronger, meaning that the B is large, the gas will exert higher pressure because the molecules resist compression more strongly. Here is the table about the van der Waals constant A and B and some boiling points of some substances. So the quantity A is somehow related to the magnitude of attractive force. For example, high A value leads to the higher boiling point. So meaning that if the liquid goes to the vapor, they need more energy or more heat, so meaning that the higher boiling point. However, in the case of B, the repulsive interaction coefficient, it is difficult to interpret, although B is supposed to be the proportional to the size of molecule. So actually, it is a little bit difficult to expect real gases' behavior from this van der Waals equation. But the advantage of this equation is that it is analytical and allows some general conclusion about the real gases. For example, first, the perfect gas isotherms are obtained at high temperature and a large molar volume. So this means that if the temperature is high and the molar volume is large, the first term is much larger than the second term, so which means that this second term becomes negligible. So it becomes more like a perfect gas. And also the large molar volume reduce this Vm minus B into Vm. This means that it becomes like a perfect gas as well. And the second feature of this equation is that the critical constants are related to the van der Waals coefficient. So in this plot, as you can see that at the critical point T is equal to C, the inflection point exists. The inflection point is 변곡점이고요, 한국말로 하면은. So when taking the first and second derivative at critical values leading to the zero values according to the mathematics. So it is just a mathematics as well finally. Then you can get the critical constant and compression factor here with the expression A and B, and the compression factor is predicted like a critical pressure and a boiling pressure divided R and a critical temperature like this. So you can just calculate it and with using this one, and then first and the second derivative becomes zero. Let's move on a different subject. So a fundamental technique in science for comparing the properties of a different system is to establish a relative scale based on the key fundamental property. So in the case of gases, critical constants serves as a characteristic properties that allow us to define dimensionless reduced variables for the compression. So this reduced volume is, let's see, the molar volume divided by the critical volume, and the reduced pressure is a pressure divided by critical pressure, etc. For the temperature is same. So with using this one, we can predict some gas molecules' behavior regardless of their property, which is implies the principle of corresponding states. So let me explain this principle of corresponding states. This is that all real gases, when compared at the same reduced volume and reduced temperature, shows the same reduced pressure. So this principle implies that gases with different molecular structure can exhibit a similar behavior when analyzed using their reduced properties, providing a more general way to study gas behavior. So if you see this plot, the compression factors of four gases is plotted using the reduced variables. So you can see that here this number is reduced temperature, TR. And you can see that in this case, all real gases follows the same line of the compression factor respect to the reduced pressure. So this is an example of a principle of a corresponding states. So different molecules follow the same line when we plot the reduced pressure versus some random variables. In this case, it is a compression factor. source of van der Waals equation is expressed in terms of the reduced variable. So it is also simple math using reduced variable and a critical constant. And finally, one important result is that in this form, the van der Waals equation no longer contains the constant A and B, which represent the molecular property. So this means that the equation applies to all substances regardless of their molecular property. So an important consequence of this formulation is that when isotherms are plotted using reduced variables, they produce the same curve for all gases. So this is also content of corresponding state. So like a visualize, we can just remember this plot for the principle of corresponding states. So compression factor that does not use the reduced variables. You can see this plot. Each gas has a different curve rather than a single curve. But when we use the reduced values, there is a single curve regardless of molecules. 일단 챕터 1은 여기서 끝났고요. 정리를 한국어로 해드리면은 그래서 이제 챕터 8 같은 경우에는 상태 변수 state variable이라고 해서 뭐 amount of substance and volume, pressure, temperature에 대해서 이제 공부를 해봤고요. 이제 이거는 이제 슬라이드 보시면 아실 거고, 그래서 뭐 scientific definition도 우리가 했고, 이제 세기 성질, 크기 성질이라는 게 있는데 이게 intensive property 아니면 이제 extensive property라고 부르는 건데 제가 아마 챕터 1에서 말을 안 한 것 같아서 이제 여기서 말을 하겠습니다. 그래서 만약 샘플을 아주 작게 잘랐을 때 그 작은 샘플과 오리지널 샘플이 어떤 일정한 값을 갖는 성질은 이제 intensive property라고 하고요. 뭐 예를 들어 온도, 압력 이런 거라고 말할 수 있겠죠. 그래서 이제 뭐 이제 작은 샘플이나 혹은 이걸 뭐 이렇게 크게 만들었을 때 큰 샘플, 오리지널 샘플을 비교했을 때 온도는 이제 똑같을 거잖아요. 그리고 이제 extensive property 같은 경우에는 이제 오리지널 샘플을 작게 잘랐을 때 이제 그 하나의 작은 샘플과 오리지널 샘플의 어떤 프로퍼티가 이제 다른 값일 때, 예를 들어 뭐 우리가 생각해보면 양이나 뭐 부피, 대표적인 이제 부피가 다르겠죠. 조그만 거랑 큰 거랑. 그래서 이제 그런 식으로 프로퍼티에 대해서 나눠서 생각하시면 될 것 같고요. 그래서 이제 상태 방정식이라고 해서 state of equation에 대해서 배웠었고, 이제 perfect gas를 이 상태 방정식으로 어떻게 표현하는지 이제 PV NRT라고 해서 우리가 이제 이 다양한 기체 방정식이 있는데 이거 같은 경우에는 이제 어떤 시오리가 아니라 실험적으로 밝혀낸 바입니다. 그래서 이 실험적으로 밝혀낸 바를 다 모으고 그다음에 이제 기체 상수 가스 콘스턴트를 도입함으로써 PV NRT라는 것을 이제 완성을 시킨 거고요. 그래서 이제 이거 같은 경우에는 어떤 마크로스코픽 뷰인데 우리가 이제 마이크로스코픽 뷰에 대해서 설명했을 때 뭐 예를 들어 보일 버튼 같은 경우에는 기체가 압축되고 뭐 부피가 감소해서 결국 일정 시간 동안 벽에 부딪히는 분자 수가 증가하고 그렇게 되면 이제 힘이 증가하겠죠. 그럼 이제 압력이 증가한다. 그래서 보일 버튼 같은 경우에는 P가 이제 V의 볼륨에 반비례한다라는 것을 우리가 이제 어떤 분자 수준에서 설명하는 건데 이것처럼 그 어떤 식을 봤을 때 분자 수준에서 어떻게 설명해야 될 것인가를 이제 공부하는 게 이제 피지컬 케미스트리이기 때문에 그거에 대해서 또 그러니까 생각을 해보시면 좋을 것 같고요. 그 다음에 이제 제가 어제 키네틱 모델 해갖고 이제 그 칠판에 쓰면서 했었죠. 그래서 이제 이 average speed 같은 경우에는 이제 temperature의 어떤 템퍼러처와 릴레이션을 갖게 되고 이제 PV도 이런 기체 분자 운동에 의해서 관계식을 구할 수 있다라는 것을 밝혀냈었고요. 그 다음에 이제 실제 기체에 대해서도 공부를 했었고, 이제 실제 기체 같은 경우에는 우리가 아시다시피 이제 기체 분자의 볼륨이 있게 되고, 그리고 이제 분자 간의 분자 사이에 어떤 매스가 존재하기 때문에 이제 인력이나 이제 반발력이 존재하게 됩니다. 그래서 그것에 의해서 perfect gas와 리얼 가스가 다르게 되고, 이 리얼 가스의 디비에이션을 표현하기 위해서 뭐 압축 인자 컴프레션 팩터에 대해서도 이제 정의를 내려서 공부를 했었고요. 그다음에 이제 그거를 좀 더 잘 표현하기 위해서 뭐 비리얼 상태 방정식에 대해서 또 이제 공부를 했었고, 그걸 어떻게 표현하는지, 또 이 리얼 이퀘이션이 표현될 때 이 perfect gas 이퀘이션이랑 어떤 관계를 가지는지에 대해서 공부를 했었습니다. 그리고 이제 반데르발스 폴스, 아마 많이 아실 것 같아요. 반데르발스에 대해서. 이제 그래서 반데르발스 상태 방정식에 대해서도 이제 리얼 가스를 고려할 때, 리얼 가스의 프로퍼티를 고려할 때 이걸 어떻게 표현해야 되는지, 그리고 어떤 뜻을 나타내는지, 뭐 A는 이제 attractive force에 의한 팩터라고 보면 되고, 이제 B 같은 경우는 실제로 이제 그 분자들이 볼륨을 갖고 있기 때문에 어떤 repulsive force에 의한 팩터라고 이제 생각을 하시면 됩니다. 그래서 이제 뭐 수학적으로 이제 이런 거는 그냥 제가 아마 그럼 숙제를 내서 이걸 이제 수학적으로 푸는 법을 한번 써보면서 반데르발스에 대해서 공부를 해보시면 될 것 같고요. 그 다음에 이제 reduced variable이라고 해서 이제 the principle of corresponding state가 이제 대응 상태 원리라는 건데, 어떤 우리가 이제 몰레큐라들 사이에 이제 프로퍼티가 굉장히 다르잖아요. 뭐 예를 들어 하이드로젠 다르고 옥시전 다르고. 근데 그것을 이제 하나의 어떤 variable을 이용해서 표현함으로써 그 특징들을 생각하지 않고 하나의 variable, 그러니까 하나의 싱글 커브로서 구해낼 수 있어서 이걸 이제 좀 더 쉽게 compare 할 수 있다는 게 이제 대응 상태 원리를 쓰는 것의 장점입니다. 네, 그래서 이제 챕터 2는 이렇게 끝났고, 혹시 이거 PPT도 올려주시길 바랍니다. 네, 알겠습니다. 그러면 이거는 제가 수업 끝나고 올릴 거고, 이제 각 챕터 끝날 때마다 이런 식으로 한글로 정리를 한번 해드리는 게 좋을 것 같네요. 네, 점점 충격을 안 하시는 분들이 이렇게요. 이창재. 그래서 다시 영어로 써볼게요. So in this chapter, we will learn the basic concept of thermodynamics. 네, 하기 전에 혹시 연력학을 1학년 때 공부하나요? 이번 학기 연력학 좀 하나요? 알겠습니다. Then, for example, basic concepts such as work, heat, and energy, and kind of internal energy or enthalpy. And then you're gonna learn the thermochemistry, which is the study of heat transaction during the chemical reactions, and also state function and exact differential, and finally the adiabatic changes. So then what is a thermodynamic? As you already learned, thermodynamics studies the effects of work, heat and energy in the system. But the thermodynamics is only concerned with the large-scale observation, such as like a macroscopic view. There are important laws of thermodynamics. For example, Zero's law is about thermodynamic equilibrium and temperature. So this states that if two systems are in thermal equilibrium with a third system, they are also in equilibrium with each other. So the three systems are in a thermal equilibrium according to this Zero's law. And the first law is the law of energy conservation, which states energy cannot be created or destroyed, only transferred as work or heat. Finally, the second law introduces the concept of entropy, a measure of disorder or energy dispersion in the system. So here are the factors about thermodynamics. It is a macroscopic science regarding pressure, temperature, or volume, but it is not based on the specific molecular model, and also it helps us predict the direction and the extent of chemical reaction, but it does not tell us about the rate of process, which is kinetic. So it is only about the thermodynamic, about the chemical reactions. So for the purpose of thermodynamics, the universe is divided into two parts, the system and the surroundings. So the system is the part of the world of interest, such as a reaction vessel, an engine, an electrochemical cell, or a biological cell. And the surrounding are the region outside the system, and the surrounding is where the measurements are made. So the type of system depends on, so there are many types of system, and the types of system depends on the characteristics of the boundary that divides it from the surrounding. So let's see this type of a system. If matter can transfer through the boundary between the system, energy and the matter can be transferred through this boundary between the system and surrounding, the system is called open. And if matter cannot pass through the boundary, the system is called closed. So this system allows the only energy to flow. And finally, the isolated system is a system that has neither mechanical or nor thermal contact with its surroundings. So there is no transfer for the matter and the energy. Yeah, so let's do operational definition of work, energy, and the heat. Work is done to achieve motion against an opposing force. For example, raising a weight against the gravity, expansion of gas, pushing out of the piston, chemical reaction in the cell leading to an electrical current that can drive a motor or be used to raise a weight like a battery. And the energy of system is the capacity to do work. So when work is done on the isolated system, the capacity of the capacity of the system to do work is increased. For example, when compressing gas or winding a spring, then the system stores the energy to do work, and when the system works, it loses the energy. So you may learn work in physics. For example, in a classical mechanics, work is defined as force multiplied by distance. However, in thermodynamics, work covers broader range of processes such as mechanical work, electrical work, expansion work, something like this. And here is the energy transfer as a result of temperature differences, but actually that our boundaries permit the transfer of energy, even though there is a temperature differences between the system and its surrounding. So the dithermic boundary is a boundary that permits energy transfer as a heat, like a C and D. You can see that energy or a heat transfer through this boundary. And adiabatic boundary is a boundary that does not permit the energy transfer, like A and B. So when the endothermic process occurs in this adiabatic system, the temperature falls. The endothermic process is a process where the energy is acquired as a heat, for example, the vaporization of liquid to the gas. But while this exothermic process, which is the process that releases energy as a heat, occurs in adiabatic boundary, then the temperature rises. However, in the case of a dithermic boundary, the energy can be transferred as a heat, so the temperature remains same in these conditions. Even I said that the thermodynamic deals with the observation of work system. Actually, it is enriched by the understanding of a molecular origin of this observation. So in molecular terms, is the transfer of energy that makes use of this disorderly random molecular motion in the surrounding, and this random motion of molecules is called summer motion. And when energy is transferred to the surrounding as heat, the transfer stimulates the random motion of the atoms in the surrounding. But in contrast, work is a transfer of energy that makes use of organized motion of a molecule in the surrounding. For example, these atoms shown here may be part of the weight that is being raised. So there is a difference between energy transfer as a heat and work for the molecular behavior. So let's keep in mind these differences. Now let's move on an important concept, which is internal energy. So this internal energy is the total energy of the system, including the total kinetic and potential energy of constituents. So please remember that this internal energy is purely internal. It means that it does not include the kinetic energy associated with the motion of the system, such as a translation motion of the gas container, or the potential energy due to the external fields, such as a gravitational or electrical potential energy of the system. So it is about the molecule or internal energy. So instead, it only accounts for the microscopic energy within the system, like I said, including molecular vibration, rotation, or the intermolecular interactions. So now let me talk about some features of the internal energy. The change in internal energy is delta U when the system changes from the initial state I to the final state F of the internal energy. Because of that, the internal energy is a state function, meaning that the internal energy is a property with a value that depends on the current state of the system, and this means that it is independent of how the state has been prepared. So in other words, internal energy is a function of variables that determine the current state of the system. So changing any of state variables such as pressure, temperature, or other things changes the internal energy, regardless of how they prepared. And the internal energy is an extensive property of a system, which I mentioned that the property depends on the amount of substance present. And the unit of this internal energy is joule, and the molar internal energy here, UN, is joule per mole. So U divided by N. I already explained the extensive intensity property, so let's skip this slide. So in the molecular point of internal energy, so a molecule has a certain number of motional degree of freedom, such as translation, rotation, vibration. So many physical and chemical properties depends on this energy associated with each of these modes of motion. So for example, a chemical bond might break if a lot of energy is concentrated in it as a vibrational motion, between this molecule. And this occurs when the molecular vibration becomes strong enough to overcome the bond strength and leading to the bond dissociation. So I explained this part. And the other one is the equipartition theorem, which can be used to predict the contribution of each mode of motion of a molecule to the total energy of a collection of non-interacting molecules. For example, perfect gas. So this each of motion means translational, rotational, vibration, and it contributes the total energy of a perfect gas. This means that the equipartition theorem. So accept this state without any derivation. So for when the temperature is high enough, there is a simple way to find the various energies through this equipartition theorem. So for a sample at thermal equilibrium, the average value of quadratic contribution to the energy is 1/2 kT. So this quadratic contribution is a term that is proportional to the square of the momentum divided by 2m. For example, let's consider the monoatomic perfect gas, which has only translation energy. So kinetic energy is, as you know, 1/2 mv squared over xyz, and each square of the momentum is 1/2 kT by this equipartition theorem. And finally, the kinetic energy of total is equal to 3/2 kT. So therefore, the total energy of a monoatomic perfect gas is 3/2 kT, where n is total number of molecules, and this becomes 3/2 nRT due to this n is more multiplied by this Avogadro numbers, and R is equal Avogadro number multiplied K. So therefore, the molar internal energy of this monoatomic perfect gas becomes UM at T is UM at 0 degrees Celsius plus 3/2 RT. So in this term, as you can see that there is no volume variables, meaning that the internal energy of perfect gas is independent of volume it occupies. This is because there are no intermolecular interaction in a perfect gas, so the distance between the molecules has no impact on the energy. So in other words, the internal energy of interacting molecules in condensed phase has a contribution from the potential energy of interaction. So it is only case for monoatomic perfect gas, because a diatomic perfect gas or other molecules has a different mode of motion, so that makes this kinetic energy different. So just remember, like, this is only for the monoatomic perfect gas. So equipartition theorem, 이거 같은 경우에 이제 등분배 법칙이라고 하고요. 한국말로는 말씀드린 것처럼 이제 평균 에너지가 하나의 운동 자유도마다 모든 모션마다 1/2 kT가 된다는 법칙입니다. 그래서 이걸 이용해서 모노atomic perfect gas, 그러니까 트랜슬레이션 에너지만 갖고 있는 그 모노atomic perfect gas의 kinetic 에너지를 이제 x, y, z 이런 식으로 나타낼 수 있는데, 요거 하나당이 모두 이제 1/2 kT니까 이게 이제 다 세 개 하면은 3분의 2 kT가 되게 되는 거죠. 그래서 equipartition theorem 그런 뜻입니다. Yeah. So let's talk about the formulation of the first law. So actually, it is based on the experiment. So experiment shows that if a system is completely isolated from its surrounding, meaning it cannot change energy or matter, then the internal energy stays the same. So this observation is known as the first law of thermodynamics, which states the internal energy of an isolated system is constant. So mathematically, the first law is written as the internal energy changes is equal to the Q plus W, where this internal energy changes, Q is heat and W is work. And this equation shows that heat and work are two ways to change the internal energy of the system. So this means that we can change the internal energy U by applying either Q, like a heat, or work from a surrounding to the system. So let's see the design convection for work and heat. If the energy is added to the system, both Q and work is positive, and if the system loses energy, both Q and W are negative. So this means that the energy transfer as work or heat is always viewed from the system's perspective. So when the system does work on its surrounding, it loses so this work done on the system by the surrounding, that work done by the system. So like when the system does work on its surrounding, it loses energy, meaning its ability to do more work decreases. That's why the work done by system is negative. And the sign of heat can be understood by intuition, like if the system absorbs heat, its energy increases, so Q is positive here. And if the system releases heat, it loses energy, so Q is the negative. 여기는 이제 좀 말할 게 많아서 오늘은 수업은 여기까지 하겠습니다.